Okay, so let's see what it says. Use a function generator. All right, so now let's all go to TinkerCAD so we can start doing this ourselves. So create ourselves a new circuit. Amazing Vihelmo Hongo, huh? Ho. Um, it's probably a good idea to name this something else, especially with your. Well, I guess you don't have to put your own name in it because I can tell. So let's see. This is 1200 03 Oscope Lab. All right, so we go up here and we have components. So switch it to all components. And scroll down. And might as well bring out a breadboard. Yeah, mini will work. And I don't know, do we need a multimeter? Well, yes, we're gonna use a multimeter and a power supply. So we have a function generator and we have an oscope. We're gonna need two of them eventually, so we might as well bring out two of them. Alright, so make sure you make little notes to yourself in your logbook. We switched over to TinkerCAD. Oh, and there's a really convenient way to take screenshots. I think that, yeah. So there's an export, but you click share and you can take snapshots. And I like, oh no, you don't have a choice. It has to be PNG. But you can take screenshots. I don't know if you guys have played with it. There's ways to rotate components, add notes. They added these two little doodads here lately. Okay, so let's see what it says. All these settings. Okay. So let's see. It says to make it in the kilohertz range. Okay. So that's one thing you can't. This property box you can't move around. That's weird. Well, 1 kilohertz. Why don't we make it something oddball? 1, 2, 3, 4, and we want a sine wave. And I think we want offset to be half of the amplitude. We'll see in a minute. And let's see. So let's connect our reds together. And I like to make this red. And let's connect our blacks together. We've been using TinkerCAD, of course, so you know something about it. You know this is new now, this changing colors like that. So the TinkerCAD oscilloscope is not quite as useful, but you can work around it. So we start the simulation, and let's wait a moment, see what happens. So, and you notice it's really tight, so that means that we have to change the time per box. So it says 100 milliseconds. Let's try 10. And wait a little while. And it could, oh, I was going to say we might have to, yep, it did change. Let's wait. Now maybe we can be impatient. We can stop it and restart it. Aha, so still don't see anything. I do notice that we want to change this to 0, the offset. Gotta stop it first. I thought you could change it in the middle. What if we just turn the knob? Yeah, that's right. But it's hard to get it to be 0. And so, oh, there it goes. Okay, so now you see it's centered. And let's see if, let's change it to 1 millisecond per box. Oh. Voltmeter is telling me to shut it off. Okay, nice. So now we're getting there. So notice that it says 10 milliseconds on the oscilloscope. And you can't change its size. You can't, there's no way to change, like move it around. So I want to go to 0.1 milliseconds. Not quite. So now I'm going to try 0.2 milliseconds. Good. Now I'm happier. So the trouble here now is that it's a little tricky to count numbers of boxes. But one thing to notice, it says 2 milliseconds on the bottom. And then there's 10 boxes, so we notice it's 0.2 milliseconds per box. And now we know how there's a relationship, because the problem is here, you see that there's no way to know what's the volts per box other than it says 10 volts there. And we know there's 10 boxes. So it's 1 volt per box. And notice that the peak to peak is 5. We set it to be that. And we can verify it if you count boxes. And one thing you can do, you can zoom in on this up here. So we can move it around a little bit. And I guess one thing you could do is you could do something like this. Although we'll just pick easier to use numbers, but I'm always trying to see if I can do something better. It's just something I can't help myself. And now my trackball needs cleaning. Yeah, it's always something. Like I'm spinning the trackball and nothing's happening. It's always something. Blow a little air in there. See, quick little wipe. Oh, there it goes. Oh. Right, so now in principle, I don't know what. Oh, it doesn't have the ability to draw straight line, rigidly straight lines. But see, I can't slide it back and forth. So this is slightly behind, and this one is exactly on. 1, 2, 3, 4. So, and then it's 2 milliseconds, 0.2. So 4 boxes times 0.2 milliseconds per box. And that's going to equal 0.8 milliseconds for the period. And if you do a 1 over, you're going to get about 1000 hertz. Now, does everybody see? So my advice for doing the voltage, because in the case of the data we have to take, that's the most important thing. So one nice thing about the sim is the sim you can do amplitude. For an oscilloscope, you always want to do peak to peak because you never can be guaranteed that the wave is centered. But with the sim you can. So we can count, where is it? Yeah. 1, 2, and we can easily see that that's half. So we got 2.5 boxes and 1 volt per box, so vertically. So that works out to a V amplitude equal to 2.5 volts. The cursor disappears on me. It's hard to see where it was. And of course, then the V peak to peak equals to 5 volts, which is just what we set it at to begin with. Okay, so here's what I want you to do in your notebooks. I want everybody to set this voltage here to 6.8. Okay, so I want everybody to make a sketch in their logbook of this screen with these numbers. And I want you to explicitly write out what is the measured amplitude and peak to peak. So I say, first you say, okay, here it is. And I think that it's this many volts per box, and why? Then I say the amplitude equals this, and why? So wait a couple minutes. And of course, we hope that we're going to get of the amplitude equal to 3.4 volts, and we are going to see then we should get a V peak to peak of this. So write it out. It's just a couple steps, 3 steps maybe. If you have the ability to make a screenshot to print out, you could add that later. Thanks. I hope so. Okay. Excuse me. All right, so we're going to skip this part about connecting these guys together because we don't have real instruments, and I have to assume that the simulation is going to have a perfect voltmeter. So another thing I want to see is unknown signal right again. That's for another time. And I want to jump into part H, but we're going to do it differently because I just think it's kind of dumb the way they have this set up, and I can show you a much easier way that you'll understand much better. Okay, so unless people protest they haven't finished this little exercise I asked you to do, I'm going to plow ahead. Okay, so we're going to stop the simulation. So we're going to now do, and next week also, I'm going to get you guys set up here. So we're going to do a study of circuit elements, and we're going to study the AC characteristics of circuit elements, and of resistors, which we know something about, and capacitors. I don't know if you guys are getting to inductors, but we'll talk more about them next week, just to make sure that everybody knows exactly what an inductor is. So first thing we need is to we're gonna set up a different test circuit than what they show. And the first thing we need to learn about is something called a voltage divider. if I, oh, here it is. Okay, so first, we need to learn we have some concepts. So, voltage divider. And in fact, if we had been doing this in the real lab, we would have, with the black paper lab, we would have used a voltage divider, and you'd have an idea of what it is, a better idea. Excuse me. And it's pretty straightforward. So if we have some supply voltage, and we have an output where we put our measuring device, and so this is R2, R1, so just in case you guys don't remember this, if I had a power supply and then I had this red out terminal, and or maybe I haven't shown you this. I get these glasses mixed up. So I connect the red here, and I connect the black here, so that's just simply the return. So how do I calculate V out? Well, all right, first thing is, this is, if I say I have the power supply, and if I have R1, R2, we see that R1 and 2 are in series. So then we know that I total equals the voltage of the power supply divided by R total, which equals R1 plus R2. That's not so. Oh, sorry. Over V power supply. So we're going to call that V in from now on. And if you think about it for a minute, if I measure the voltage, and I suppose if we want to be really fancy, we'll put a wire there. So if we want to put our voltmeter here, we know that the voltage across R2 is going to be I2 R2. But we also know that since it's a series circuit, that I2 equals I total. So then V out equals I total times R2. So I can solve for I total equals V out over R2 So then I can set these two guys equal to each other because they both equal I2, I total. So V in over R1 plus R2 equals V out over R2. So this is one of these instances where we have this is voltage divider background. So then we see that V out is going to equal R2 over R1 plus R2 times V out. And what did I say? V in, of course. Remember, rule number 1, the professor is always right. And rule number 2 is that if the professor is wrong, see rule number 1. Okay, so next is we're going to create a voltage divider and test it. This is the part where you exercise your equipment. That's how we talked about this at the beginning of the semester, and test it. So if we set R1 equal to say 500 ohms, and we set R2 equal to 250 ohms, and we set V in equal to say 10 volts, then we expect V out equal to R2 over R1 plus R2 times V in. We expect it to be 250 divided by 250 plus 500 times 10 volts equals 250 over 750 times 10 volts. And I guess that's 1/3, which is unfortunate, but what can you do? And I might have made a mistake. Check me. Oh, we're running out of time. That's fine. We're almost home. So yell if you want me to go back. So let's try testing out our voltage divider. So we need 2 resistors. And let's see, R1 we said is 500 ohms. And R2 is going to be 250 ohms. Right, everybody should be doing this themselves. We have a power supply. And I want that to be 10 volts. And let's see, we need our schematic here. I might as well just draw it on there. It's always good to have it in front of us when we're wiring something. So we got a power supply, and we want to go to resistor, back, 1, R2, and then we want to take our voltmeter and attach our voltmeter like this. Okay, so we come out of the power supply and we go to, oops, R1. Then out of R1, we go to R2. And then out of R2, back to the power supply. And then we can connect the power supply to the common point. And then we want to put it to the measuring point, which is in between the two. Oh, something got weird. Okay. Dun 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 dun. Let's see what happens. Ooh, huh? 3.33 volts, just as we predicted. Excuse me. So everybody should now, in their logbooks, pick your own R1 and R2. Pick R1 and R2 of your own. Or at some point, maybe you can hold off. You can do this on your own time, as we're running out of time. Pick an R1 and R2 of your own, and predict the out, and verify it with TinkerCAD. Write it down. Write it all out. Okay. So here's what we're going to do to take data. We're going to use a voltage divider. But now we're going to use the function generator. So now this becomes our STD, our standard. This becomes the good old device under test. So there's an R standard, there's an R DUT. Of course, that was kind of dumb because I'm blocking my output dot. And we have a V out. And of course, we have V in. And let's see our formulas. V out equals R2 divided by R1 plus R2 times V in. So what we can do is we can change this to V out over V in. So now this is our testing device and our background of our testing schematic. R2 over R1 plus R2. It's going to be a little dicey. This is where I should have been a little more prepared, so I'm just going to save myself some writing. I'm going to call that parentheses for the time being. R1 plus R2 equals R2. Ah, right, I see what I could have done better. No, I'll just keep going through. For the first test, they were 500 and 250. I asked you guys to pick two of your own and calculate. Yep, good, you got it. Sorry to go too fast. All right, so like I said, I realized I could have done this algebra better, but R1 plus R2. So that becomes R1 equals R2 minus parentheses R2. So that's R2 to 1 minus parentheses. So then at the end of the day, I did this too messy, but I have to live with it. At the end of the day, let's see, so it's parentheses R1 equals R2 times 1 minus parentheses. So R2 equals what a mess. V out over V in, R1 over 1 minus V out over V in. So that can be better. All right, let me just scratch it in my notebook quickly. So, no, doesn't. It's got to be easier way, but I don't see it at the moment. But anyways, if we can measure V out, V in, we can see that there's a possibility to get R2, which is, of course, the device under test. And you'll forgive me for that mess. Maybe I should have set it up the other way around. Let me think about this for a minute. I can measure the voltage across our standard and the voltage across. Oh well. We're almost out of time. So here's what we're gonna do. I've been doing this in my basic electronics class, so I thought, oh, piece of cake, right? So we should be able to set a V out, let's say, V in is 10 volts peak to peak. We can set an R1 or an R, which is now our R standard. And let's call it 100 ohms. And now we're going to measure some DUTs. Which is our R2. So we need to create a table of, and we're going to measure V outs. And then we're going to do it for a bunch of frequencies. And this should go 50, 100, 500, 1000, 2000. Come on, Ari. 3,000, 10,000, 20,000, 30,000, and 100,000. There we go. And then we're going to measure, we know what V in, we're going to measure V out. And there's going to be for a resistor, a capacitor, and an inductor for the time being. Those are our three devices under test. We're running out of time, so I'm going to show you this. So we no longer need the voltmeter. So there's our R standard, and we say we want that to be, where's the window? There it is. 100 ohms. And we need an inductor. So this is going to be our test. We have a test resistor. And see, you can spin this by going up to the upper left here, rotate. Whoops. And we have, and then we need a capacitor. And of course the capacitor is going to give us a hard time, but we'll just put it like that. What's the second resist? We can stick with 250. And then this guy should become, welcome, make it 10 millihenries. Right. Up here in the upper left, see it says there's a rotate. So anything you want to rotate, you highlight it, and then you click up here. Yep, that's fine. And yeah, what's this supposed to be? What's a good value for this? This should be 10 times 10 to the minus 3. So I think this should be 2 times 10 to the minus 6. Let me just double check. I'm working my calculator, sorry. 20 exponent plus minus 9. And then square root. And then invert is right. Okay, good. That'll work. So we're going to make our capacitor 2 microfarads. Okay, so we have our function generator. Let's see how we're going to do this. Well, it looks like it'll be easier to do it like, oops. Put this over here. So this will be the return. And well, I can go anywhere. I see where the bigger board would have been better. Yep. And I also see, this could be done neater. I'm now realizing. And now I'm going to cross these wires anyway. Ha! I was trying to avoid crossing the wires. So that has to go to our R standard. You can, you can drive yourself nuts with this stuff, So one of these is going to be our total VN. And then one is going to be, and then we have to put it to the return. So this, I was trying to make it neater. I think I'm ending up making it more sloppy. So I encourage you to make this look nicer. And then across the device under test. So then this is going to go through this guy over to here. And then, in fact, yeah, I guess you have to be a little careful. So, and then this goes to the return. Wow, I could have done a much better job of making this look neat. If I practiced at a time, maybe. Okay. And then, did I do that right? Yeah, through the device under test. And then this, I can put this here, that's easy. So there's definitely got to be a better way to do this. Ha! Lord. And we can make that a different color to make it easier to see. So certainly you can get some extra points for making this better. So now we got to start at our starting frequency. And I think we said 10 volts peak to peak. So let's try it. So now we have to adjust this. So this is going to be, let's try this at 10 milliseconds. You got to do a little playing around. That works. And I want to make this one 10 milliseconds. Great. Now, you have to be a little careful. Notice this one says 20 volts. This one says 10 volts. So now, I want to measure. Now, you can do amplitude. Well, no, you can do peak to peaks is fine. So input is peak to peak. So let's see. This is... Come on. 1, 2, 3. It looks like 3.5 times 1 volt. So that's 3.5 volts amplitude. So it's 7.0 volts peak to peak. And so we go back to our table. And I would encourage you to put this into a spreadsheet. So our standard 100, our test is 250. C test is 2 microfarads, and L test is, I think I said 10 millihenries. So we did 100 hertz, okay. So this is, what did we say, 7 volts? And then watch this, we can be really clever. I'll just, now I'll do the inductor. So the capacitor is not going to help us much. We have to maybe rewire it somehow, because I can't just push the capacitor in there easily. So now let's restart. Okay, so then we see 1, 2, 3. It looks like about 3.2. So that's 3.2 volts, because it's still, oh, careful. See that? Look at that. I almost got fooled. This way you can't go too fast. It's 3.2 boxes. And now it's 1 volt, so it's 0.1 volt per box. So it's 0.32 volts amplitude, so it's 0.64 volts peak to peak. And, oh, I was like, where did that come from? Clear. And now for the inductor at 0.64 volts. And then, all right, let's do the capacitor. How can we rig up the capacitor? Stop simulation. Oh, I see. Just put a wire from here to here. Now, try again. I put this here. Right. So now it's going into the capacitor, but I have to come out of the capacitor. All right, so I see what to do. Move this, move that, and I connect one from here to here, so that one doesn't do anything until I put the capacitor in place. Now I put the cap in there. Now it goes through. Cool. Start. And now notice it's 2 volts per box. And so I see 1, 2, about 2.5 boxes. And 2 volts per box. And wow, it's the same as V in. 10 volts peak to peak. And so on. So your job for next week is to fill out that table, fill in this table, and we will go over it next time. Okay. And I'll slice up this video to show that procedure. Great. Okay, guys, sorry to go over time. I'll see you all soon. You know how to reach me. I'll also post a video about how to take it further, so then you can be more prepared for next class. And to give you a little break, I won't record. Well, there's Lab Day Notebook today, but I won't require any checkpoint or anything next week, so you can focus on the cardiovascular report and cardiovascular final notebook. All right, so I'll see you all soon, guys. You're welcome. All right, guys, I'll see you all. Yeah, you can't see me, but thanks for coming. You're welcome, guys. See you soon.